Okay, let's now move to the application of the wavelet transform. Some of the applications, okay? So the first one is signal denoising and compression. We will look first at signal denoising. I have a noisy signal, okay? And I want to uh, filter out the unwanted parts of the signal, okay? This is actually a signal that you can filter using just a low pass filter maybe, or an aberration. Low pass filter is also an aberration filter, or you can design a specific filter to design this. But the output or the filtered signal will always have some um, fluctuation, let's say, will not be filtered the way we want. Another way to do so is to use the discrete wavelet transform, okay, to decompose the signal, okay? And after that, you will have signal at different levels. And from there, you can decide about the threshold, or let's say the this the component of the signal that doesn't contribute to the original signal, the clean signal, okay? And from there, I can reconstruct the signal of interest. This way, we use the inverse discrete wavelet transform. And the clean signal will be something like this. Let's talk about the other applications, and then we go to MATLAB to look at them further, okay? So this is signal denoising. This is a Doppler signal, which is noisy in this case, using the discrete wavelet transform, and its inverse, we can reconstruct the clean signal, okay? And the discrete wavelet transform is very useful when it comes to image denoising and compression, okay? This is just image showing the whole workflow of compression and compression. We'll only look at these parts where we use the discrete wavelet transform, and for the reconstruction or and compression, where we use the IWT or the inverse of the WT. We have an original image here. We'll do the multi-level 2D wavelets. I didn't talk about the 2D wavelets. It's the same concepts. It's the same workflow. Nothing new when it comes to 2D version of the wavelet transform. It's the same basically as wavelet Fourier transform. So, but this time we have a 2D signal, and that's the only difference. The 2D signal, I mean here an image or a scaleogram or something like an image. Okay. So we have the original image. I will decompose it to look at at different levels. Then I will threshold and reconstruct the compressed image. Okay, and it will be actually the same as the original image, but with less redundant information. Another application is time-localized filtering. Time-localized filtering. Okay, this is another demo. Let's now go to MATLAB, okay, and learn about the noising and compression of signals. Signals here, I mean time series or images. So the workflow for both is to decompose the signal, some thresholding, and after that, the reconstruction of the signal. Let's first look at the noising signal. I will clear the workspace. Then I'm just loading here this noisy Doppler signal. It's in MATLAB, so I don't need to specify the directory of it. It can be found in documentation, and I'm visualizing. This is the Doppler signal. This is the same we saw in the slide. Okay. What I need to do first, I will just analyze the signal. I want to learn about the signal, see what's the frequency content and how it looks like in time frequency domain. Okay, so I can use the wavelet transform, the continuous wavelet transform, to visualize the time frequency information. And this is how it looks like, this noisy signal in uh, in the magnitude scaleogram representation. Yeah, it's clear that we have some noise here in the high frequency uh, part of this scaleogram. Looking here, you can see some noise here and some noise again here and here, and maybe also some in the low frequencies. Okay. What I will do now, after I learned about the signal in time and frequency domain, and I can clearly see that I have some noise, I want to denoise it. So MATLAB made it easy. You have functions, this function called dd camp. So this decompose the noise compress. So the first D is decompose, then this is the noise. Oh, sorry, this D is maybe discrete. Anyway, this DEN is the noise, and this compress means that this function can be used for denoising data or for compression. The second step in this workflow is to reconstruct the signal. When we say reconstruct, we first need a threshold. So what does this function do? It returns the threshold and also some other outputs here that we're going to use for another function. And this function now is called WDEN, DEN CMP, which means this is wavelet and this is the noise and compress. So it reconstructs the signal based on the output of the previous function. So you're gonna say, okay, what does this function, these two functions does? They do the wavelet transform, the DWT and the IWT. Maybe it's a different implementation, but this is the concept of these two functions. So you don't need to write the code for DWT and then you decide about the threshold and all these things. All you need is these two functions to denoise the signal, then sorry, to decompose the signal, then reconstruct it using this output. Okay, let me run it, and here we go. So this is the noisy data in blue, and the noisy data, this dashed red line. It's now smooth. Okay, maybe this is a good filtering process. Now I can go ahead and automate this code. For example, I can write a function that I will pass as input these uh, noisy signals, and in the output I will get the clean or the filtered signal that I will maybe use for training some deep learning or machine learning model. So this is the pre-processing application of DW and its inverse version. The function um, W then, okay, this is not correct. This is the noise. Okay, this is the same function. Okay, it performs the different signal denoising steps. Okay, we can visualize that. So this is another function. It's not the same way as this, but I can say that this is a function that regroup the two functions we saw before. So it does the decomposition, the thresholding, and the reconstruction. And here I'm comparing the results of different approaches we used. So this is the one we have in red, and I'm plotting the signal to noise ratio. Okay, so the noisy Doppler signal it has a very low, we cannot say very low, but it is low comparing to the other SNR we got after the noise in the signals. This is the first approach. We use the two function, and this is the SNR for the second approach, using one function for decomposing, for thresholding, and for reconstructing the signal. Okay, let me close this. There is another way to do so, is to use the Wavelet's Denoiser app. Okay, this is an app that you can find in Wavelet toolbooks. Okay, it's an interactive way to do the different steps we have done before, and by passing the the signal that you want to filter or the noise, you will get the canvas populated with the signal, and the noising process will run automatically. But you can still change the parameters or the settings, such as the wavelets. Okay, you can use the dB, and when you change, you need to run. Okay, I'm not happy with these wavelets. It doesn't give the a good filtering result here. As you can see here, changing the wavelets or the function gives it is not correct here. This is like a scaled signal. It's not smooth, and I cannot actually use it for training some machine learning model, because I believe here some information is missing. Okay, but let's change again. Use the wavelets and the noise and see. Again, this is, we have some transient noise here, so this is not a good wavelet. Let's go back to our original wavelet function. As you can see here, the app wavelet signal denoiser selected the best wavelet for me. What is this? So this is another way to interactively denoise a signal using the wavelet denoiser app. Okay. And after you are done or happy with the signal, you can export it maybe as a signal, as data, or you can generate a MATLAB script if you are willing to do some automation or write a function for this pre-processing. Okay, let me close this. I don't need this. Is the code we generated. So we learned how to do that using the wavelet signal analyzer. We can also denoise images, and this is the same function we looked at before. The only difference is that we have these two, means that two-dimensional, okay? And you have the level. Level is the decomposition level of the wavelets, okay? I can run this. In the end, the image is just a signal that has two dimensions. So this is the original signal. It has a lot of noise, and our animal here is clear. We can see it in the denoised image. So the noise was removed. I can change the level interactively and see the effects of that. It's now much clearer. Okay. And as I said, DWT can be also used for image compression. We use the same functions we saw before, but wait, this is actually a different function, but it has again another version for one-dimensional signal. Okay, the first step is to decompose the signal, but I need the signal, the image. I need to load first. This is the image, the original image. And now I will decompose the signal using the discrete wavelets. Okay. And the final step is the reconstruction of the image. I'm using in this case the wden. This is the same function we used for denoising this signal. And I mentioned that this CMP means compression, so I can use it. And this GBL means global thresholding. Okay. Let me plot all these pictures here. And I'm comparing here. This is the original image. This is the compression. It still has all the information, but now it's compressed and it's now maybe with less size, and we can transmit it with low resources. Okay, this is for the compression. There is another compression called true compression, and MATLAB has a function here. It's called wcompress. Okay, it allows you to do what we call the true compression uh, of images. Okay, so what you pass here is C. C means compression, but this function can be also used for uncompression, as we're gonna see here in the next section. We have U means uncompression. The same function, we can use it for the two application or for the two processes. So what will generate, what will do, it will compress and save the file. This is the file called mask. It has this WTC, and if you want to do the uncompression, you use the same function, and you're gonna have the uncompressed signal. Let me plot it, uncompressed signal, and this is the uncompressed signal here. Okay. Maybe I can plot. Um, let's plot the mask image before compression and compare. It must be X. Okay. Let me run it. Yeah. So this is the image before compression. We compressed it, and then we did the inverse process or procedure, and we got the mask here. It looks the same, I believe. Yeah, so this is a function that has all these the wavelet based steps. I mean, here the decomposition, the thresholding, the reconstruction. It has all these steps implemented. It's one function. Just like that, you decide about if you want to compress or uncompress, and you're gonna get the result. But you need to be careful here when you pass the name, because this is for compression. Okay, we want to save it this format. And for the uncompression, you need to pass the compressed signal or the compressed image, sorry. Okay. So this was for that was all for the denoising and compression of signal and images using wavelet transform. Okay. We can go back now to MATLAB. And we have another application here. It's called time-localized filtering. I have a noise in my signal here. I cannot see it in time domain, but I can clearly see it when I plot the magnitude scaleogram. Okay, it's here. And you will maybe say, okay, Abdurrahim, you can't just apply a low pass filter or a band pass filter, and you're gonna filter out that part of the signal, that's unwanted part of the signal. But this lies in the same range of my signal of interest. If we look at the frequency axis here, okay, if we look this way, it lies in the same frequency range that's I want to have in the end. I don't want to filter this parts, this frequency information, but I don't want these parts. So I cannot use the filters we know, this classical filtering approaches. Okay. The idea here is to filter the signal using the wavelet transform. Okay. So what we're gonna do, we're gonna just decompose again the signal and localize the noise, then zero out the unwanted pixels in the scaleogram and use the EWT or the inverse wavelet transform to go back to the time domain or to reconstruct the signal. Let me go to MATLAB. This is my MATLAB. Let me close the app. I don't need it anymore. and this also. Okay, this time localized filtering. This is an ACG signal that you will find in this folder called SIG data. Okay, so here I'm just starting fresh, clearing the workspace, closing all the figure and so on. And here I'm loading, and they have this support function that I implemented. It's in the bottom of this MATLAB live script, and the inputs is my signal and the time information, and they have here the noisy signal. And if I zoom out, I can see that I have some noise here or unwanted information between the peaks. Okay. The first step to do is to analyze the signal in time frequency domain, and we learned that for non-stationary signal, it's always good to use the continuous wavelet transform. So I'm using the command CWT to analyze the signal in the time frequency domain and detect where I have exactly this noise. Okay, this is another way. This is using the signal analyzer. We saw that before. We can analyze in, can actually plot the scaleogram. It doesn't tell me anything here. Okay, but scaleogram will tell us about the signal. Maybe it will take some time. Okay, but let's go back to just the plot that's our common CWT um, gave us. Okay, this is the magnitude scaleogram. And looking at this plot, you can see the noise here. Some noise is here, but these are the information of interest that I don't want to filter or suppress from the signal. Let me see if it plots. Okay, we can see here the peaks, but they are like they are a lot. That's why we don't see any of them. I can use actually this panel here and to zoom out, to zoom in on some signals, and I will see the peaks. And this is the noise that I want to uh, suppress from my signal. Okay, and close it and save. I have already the scaleogram here, so I learned that I have some noise. Now I will use this technique called time localized. First, what I will do, I will calculate the wavelet scaleogram using the command, the same command. Now, but it now has some output, the wavelet transform matrix and the frequency vector. Let's now localize the noise. I'm using here some other tools that you can find in MATLAB to get this marker here, and now I need to select the frequency and time that I want to suppress from my signal. I press it here, and then I will go and ahead, and I will go ahead and press here. So it's like I'm localizing the noise in the scaleogram. Okay. So what I get here, I got the lower bound for the frequency and the upper bound for the frequency, and the time range we already know from the signal. So these are the index of them that we use to index into the wavelet matrix. I want to get this noise. Okay. So what I need to do, I need to index. So I'm using these indexes here of the frequency and time, and I'm getting the I'm assigning them to zeros. It's like just suppressing. Zeros means this dark blue. Okay, dark blue. Okay. Now I have the scaleogram, or I have the CWT output, which is the matrix, and I zeroed out the unwanted part of the signal. How can I reconstruct the original signal? I will use the inverse of wavelet transform. And this is the way you can do it. Okay. If you look at this, it's a signal of the same dimension as my original signal. Let's plot it. Here, this is again another function that I have in the bottom of this function of this MATLAB live script just to compare the original signal with the filtered or the clean signal. Okay, waiting for this to run, I'll show you the functions. This is for the, okay, we got the result. So this is just for plotting in time domain, and this is for extracting the frequency range. So this is the function that allow us to select the we did this before. This is the function that allow us to select or to localize the noise interactively. Okay. So this is the result of the filtering. So another application of wavelet transform is signal separation. Okay. Signal separation, and you know, I believe you all know about this ACG data. We are always more interested in the peaks or what we call the R waves. For example, in this application here, I'm trying to find the peaks, and there are algorithms that find the maxima or the local maxima or the local minima. But using only the algorithm will not help a lot. So what I will do, I will just decompose the signal and reconstruct only the R waves, and this using the wavelet transform. So before the some peaks are missing, means measured average rates will not be correct, and all the peaks, but after applying the DWT and IWT, I forgot to add IDWT, the inverse of DWT, I'm getting the R waves. So it's like I isolated the R waves from the rest of the signal. Okay, so let's go to MATLAB and see this demonstration. Now let's go to the application and signal separation. I'm using again an ACG data. Okay. So, and I'm loading it this way, the same function. Then I'm analyzing it using this time using another app called Wavelet Analyzer app, Wavelet Time Frequency Analyzer app. This is the app. This is an app that you can use to analyze without writing any single line of code. So it gives you actually the magnitude scaleogram, and you have some parameters here to choose from if you want to analyze further the signal. Okay, but I'm happy with this. I can see clearly the R waves here. Okay, but when I move to the algorithms to find the peaks, as we saw before, it fails to detect all the peaks or the R waves. So let me close this. Okay. So this is the signal in time domain. I use the app to analyze it, then I can find the peaks. There is an algorithm here implemented in find peaks function. It's called it's called local maxima, or yeah, it's an algorithm that finds the local maxima in your data. But when I apply it, I can see that some peaks are not there. So the algorithm doesn't detect them just like that. So I can actually change these parameters. It has many parameters, but it will spend many hours maybe tuning these parameters because it has many parameters, these find peaks, and maybe in the end you will not find all the peaks in your ACG raw data. Okay, so the idea here is to decompose this signal and isolate the R waves. How can it do that? I can use actually the app. So this is my app, and this is the decomposition at different levels. This is our different levels. This is the approximation, and the other levels are the details information. Looking at this, it doesn't seem to isolate the R waves, looking at the approximation, but looking at the level 4, seems like this is my R waves. Okay, so let's select this. There is a table here. You can select the level from. I will select the level 4. Okay, so this is the R waves. I can isolate them this way. Okay, and after that, when I'm happy with the reconstructed signal, I can go ahead and export it to MATLAB. There are different ways. Again, you can export it as a reconstructed signal. You can export it as a matrix, and also you can generate a code if you are about to do some automation in your code. Okay. I will just export it as a reconstructed signal, and it will have the name ACG1. I can go ahead and now reconstruct this signal. I'm just plotting it here. And I'm finding also the peaks. I'm using the algorithm together with the reconstructed signal. I can see now all the peaks. So I have all the peaks. But maybe a question that comes to your mind, maybe, are these peaks in the same location as the original peaks? Okay, let's find out. Let's see if that's a correct locations of my peaks. What I can do in this case, I can plot these peaks together with the original signal, with this signal I have here. Okay. I'm using these find peaks, but this time I'm not using it without the outputs. I have the peaks and their locations. Okay. And they have this line of code to plot together the peaks and the original signal. I don't know if you can see that I have them in the same exact location as the original signal. These are the peaks that it detected. I don't care about the amplitude of them because I want to use them for estimate the heart rates. What is important for me is the interval between these peaks. Okay, so if we find them and they are in the right location, the correct location, I can go ahead maybe and use that for um, heart rate estimation. Actually, I'm not going to do that because my script ends here, but you can use these peaks to estimate the average heart rate, and there is an equation for that. Okay. Let's go back again to MATLAB, to the slides. So one of these applications and the final application that I'm going to talk about is feature extraction. This is very important, and there's a different, or let's say slightly different wavelet transform. We call it wavelet scattering transform. It's basically based on 3 steps. The first one is the convolution of the wavelets, okay? The convolution or the wavelet transform, or the continuous wavelet transform. Then we introduce some non-linearity by applying the modulus. And finally, we apply a low-pass filter to average the signal in time domain. Okay, these are the steps, as I said. There is another way to look at this and understand it further. We call it the tree view of wavelets scattering transform. Okay, so this is my input signal. Maybe this is the ACG signal. Let's take that as an example. So the first row in my matrix of the features is just the averaging of the signal. So when we do the convolution of a signal with a low pass filter, in time domain it's convolution, but it's in frequency domain is just a normal multiplication. So what we do, we convolve the signal with a low pass filter so that we average it, and this becomes now the input of the next level or next layer. And this, what you can see here, are the wavelets at different scales and translation. And as you can see, we apply the modulus okay? And then what we do, we average again. In time domain, we apply a low pass filtering process, and so on. So this is the notation. These are the wavelets, and phi g is the scaling function. Okay, this is the averaging function, the low pass filter. You can call it any of these names. Okay, and f is the input signal that can be any of these time series or images. And there is again the 2D version of it. So the final application is feature extraction. I will show you how to just use this wavelet scattering and transform to extract the feature in MATLAB. We learned about it. It's just something like convolutional deep neural convolutional networks. Okay, it's something like that. But this time we use the wavelets for the convolution step. Okay. I have some data here. It's about compression. It's here in this folder. Okay. Air compression data sets, and they have classes, and they want to extract feature from for different classes for some learning purposes. Okay. I do have the data, so I don't need to run these parts. But for you, when I share the file with you guys, you need to run this so that you download the data. What I will do right now, I will just run this. And here I'm using an audio data store, sorry. These data store are very important when dealing with data, big data. So it allows you to manage and access the data, and it it has as input argument first the folder that you want to load using the function, and you can decide about including or not including the subfolders. I need to include the subfolders because there I have the data for my different classes. Okay, and I'm here counting the number of categories or the number of classes I have. Okay, as you can see, I have 8 classes. I can I can mm, I can I can now split this data into training and data sets. I will not go into these details now, but we're going to talk about this later in Wavelet for machine learning demos. Okay. Here I'm just plotting the data, the training set and the test set, and I'm plotting here in the time domain because these are audios. These are recording of some audios from the compressor. Okay, and we are plotting them here. Okay. Now, let's see how we can create an wavelet scattering network or a network for wavelet scattering transform. Okay, that is this class called wavelet scattering. This is not a function, but a class that you call to create an object for the network that you want to create. I mean, you have some attributes of this class that you will change according to the application that you are interested in. So the parameters here differ based on the signal length and also based on the sampling frequency of the data. Okay, I have here my signal length, I have my sampling frequency and the invariance scale. And because this is an object, we have some methods that you can apply to learn about the object you have just created. Okay, this is something similar to oriented object programming. So we have a object here. You can learn about its attributes and all these things using the methods that it has. Or you can do some other calculation using the methods that this class has. And there is a command called methods. Okay, you pass the class name. My class name is SN, and it will print different methods that you can use together with this this network, the wavelet scattering network you created. This function can be used, or these methods can be used together to extract or to learn about the objects. Okay, I used actually path and number of coefficients. Okay, now we can extract the feature from the training sets. Okay, we split the data before, guys, if you remember, to a training set and testing set. Now we can extract the feature from the training sets, and they have a function here that does that for the whole data sets, training set, or let's say the data sets, because we are calling it twice here for the testing sets. What does this exactly? I can open it. Can open it. It has as input argument the data store, and the input argument, the second input argument is the scattering network and the length of the signal and the batch size. If we don't have a folder or subfolders, we can just go ahead and use only the feature matrix method to extract the feature from our data sets. That this time will be just a single data set or a single signal. Okay, but because we have a very big data here, or very big data set with subfolders, I need to iterate on all this and process that using what we call the batch processing. So this is just a function to support the extraction of the feature from a folder. If you are doing that for a signal, you will use a single data, a time series or a signal or an image. You will use this feature matrix together with the scattering network, and here you will have the signal. Okay, and what we are doing here, we are concatenating. We are concatenating somewhere. Where exactly? Yeah, we are doing concatenation, and we are also converting to single so that we speed up the extraction of the features. I can go back to my section where I'm calling this function here, and as you can say, passed now passed the training data sets, or this is the data store, and then the network, the length of the signal, and the batch size, because we are processing many files in this case. I can run it. Maybe it will take some time, but you can speed up this process by using the GPU, or you can maybe use a par4 from these tools can be found in these parallel computing toolbooks. So they support the acceleration of your codes. We're gonna, if we have time, we're gonna see a small demo showing how to accelerate the processing of this feature extraction using a GPU. Okay, so it's running right now. Let's wait for a while. And here we go. So the input here will be a three-dimensional array. Let's say array. It's not a matrix. This is the dimension or the size of it. Okay. But we want to see this. How we can how we can do that? How we can reshape this? Let's say reshape. Okay, I'm reshaping this here. I'm doing the reshaping. But before I'm doing the permute function, just to change or to permute the array dimensions, I need this because I need to organize the features in a way that each signal or each feature signal will be very well labeled. Okay. But now I can maybe look at this by hovering on this, and you can see this is the matrix of the feature for the whole training sets. And we extracted the feature using the the scattering transform, or the wavelet scattering transform, which is very powerful extractor, feature extractor. We knew from these scientists that they developed this, that this wavelet scattering network generates independent features. And when we say features that independent, means that a good features that we can use to distinguish or to classify some data sets. We can do actually the same for the testing, but it's not required. It's actually the same. The only difference is that we are using gather, and this is the function that we use with the tall arrays. We process batch by batch, or let's say segment by segment of the data, but in the end we want to have them in the same, so we can use this gather to gather all these outputs. Okay, and this is for the wavelet scattering network.